So in this subpart of the lecture number 5 of Physics 401A, we will discuss the form of Lagrangian for a mechanical system. As you already have noticed that in our previous derivation of Euler-Lagrange equation, we did not use, or rather we did not need to use, the explicit form of Lagrangian, right? Now, need to use, right? Now, as you know that our principal objective is to find q as a function of t, and thereby deriving also q dot of t, we will try to specify the state of a system. Then we have to solve the Euler-Lagrange equation, and for that we have to know the explicit dependence of L on q dot and t. Okay. Now, we first start by using a simplistic approach for usual classical mechanical system, and that we will discuss over here. So, as we know that the governing equation of the mechanics, the traditional classical mechanics, is Newton's law. So, we start from Newton's law over here. Okay. So, Newton's law is nothing but m times the acceleration, which is r double dot, is equal to the force. And this you can write by taking scalar product, okay, on both sides with scalar product by del r del qi. Then you will have this part m r double dot dot del r del qi, that is equal to f dot del r del qi. Now, if we try to analyze this term, we will simply see that r double dot is ddt of r dot, and del r del qi we just keep it as it is. Then we can this write as m times ddt of r dot dot del r del qi minus r dot dot ddt of del r del qi. That's simply because you can notice that if you add this term m ddt of r dot dot dr del r del qi and r dot ddt of del r del qi times m, of course, then you will finally have m times ddt of r dot del r del qi. Okay. So finally, m r double dot dot del r del qi is nothing but ddt of m r dot dot del r del qi minus mr dot dot ddt of del r del qi. Okay. Now first we have to do some simplifications, and for that we have to prove small things. The first one is we have to prove this one, del r del qi is nothing but del r dot del qi dot. Okay. If it were a total differentiation, then we didn't have any problem, right? Because we know that dt with dt, they will actually nullify by the chain rule of total differentiation. But for partial differentiation, we have to prove this. Okay. So as you know, okay, here for this problem, I have specifically assumed that r, which is the position vector, is only the function of generalized coordinates and no dependence on time, no dependence of velocity on velocities. Although dependence on velocity is impossible in general, but explicit dependence on time is possible. So I leave it as a small home task to you to do all these proofs using also explicit time dependence of r. Okay. Now if you just have a look at this one, that dr vector dqi, so they are d. Okay. Then we can exactly expand as the chain rule of partial differentiation by saying this is equal to del r vector by del qi plus del summation over j, where j is not equal to I, del r by del qj dqj dqi. So this is I. Okay. This is simply the writing up total differentiation as a sum of several partial differentiation. Okay. Now you can see that if r dot can simply be written as dr dt, and that ddt can also be expanded in terms of its in terms of in terms of qy's, because there are so dr dt can be written as del r del qy dqi dt plus summation over j, again j is not equal to I, del r del qj dqj dt, right? If it is true, then you can say that this one is giving you just this one is giving you a term which is involving only qi's, and this one giving you all the other terms where I is not equal to j, the same type of grouping as they are here. Then you can again say that I am taking del qi dot of this one. Okay, so I now say that this is my expression for r dot, so I take del qi dot of r dot, r vector dot. Then there will be this type of term, so there will be del r del qi. Okay, as you can easily understand that there will be several type of dependencies over here. One will be simply del r del qi, because del qi dot, if this is acting on this term, okay, if I say del qi dot of this term, so first of all it gives me two type of terms. One is del r del qi dot, which is 1. So that's exactly this term. Okay. Then another one will give me qi dot. Now del qi dot will act on del r del qi. Okay. Now if you can see that qi and qi dot, they are mutually independent, so the partial differentiations can commute, and when this is acting on this r, as r is not a function of qi dots, so this will vanish simply. Okay. Again, I do the same thing with this term as well now. Okay. Then del qi dot will enter over here, and you will see you will have two type of terms. One is acting on this del r del qj, that is over here, that is the fourth term, and you can simply see again del qi dot can commute with del qj, and finally it will give 0 because r is not a function of qi dots. Okay, and another term will be del r del qj, and del qi dot will then simply act on this one. Now you know this summation is explicitly for j's which are not equal to I, so this will be 0 because all the q dots are also mutually independent. Okay. So finally we know that this one is simply this one. The equality is then proved. Okay. Here again I am saying that do it at home. Just now think r is also a function of time. There is an explicit dependence on time as well, and prove that for prove also this result for that. You will see the same result will be there as well. Okay. Now from 1 and 2, so that was 1, okay, and 2 was this. Now you can simply replace this one by del r dot, this one by del r dot del qi dot, and you will have this expression which is equal to mr double dot dot del r del qi. Okay. Once you have this, we will do another small proof by using which finally we have something interesting. Okay. We have to prove ddt of del r del qi. Okay. So ddt of del r del qi. Okay. That is, you just expand ddt. Now this will be del t plus summation over del qj times and also summation over del qj dots. Okay. So ddt of del r del qi will simply be del t of del r del qi plus summation over j del qj del r del qi qj dot plus summation over del qj dot del r del qi qj double dot. This one is simply 0, as you can understand. Again, this commutation, and this r is no longer a function of velocity, and this one is also 0 because of commutation, and r is not a function of explicit function of time for this case. Again, you can okay, and so you only have this equation. So this one is nothing but this equation. Okay, then finally you can write, taking this sum is on j, so you can take this del qi outside of the sum, and you have del qi summation over del qj of r qj dot, which is nothing but the total time derivative of r vector. So this is nothing but del qy dr vector dt. Okay, and which is this one. So this is written in another sense actually in this line. So here you can say, so ddt of del r del qy is equal to del qy dr dt. This is equal to ddt of r vector simply because r is a function of q's only. Okay, now do this problem also assuming that r has an explicit dependence on t as well. So the r is a function of q's and t, and prove the same result. Also for that you will see the same result will follow there as well. That means del r dot del qy will be equal to ddt of del r del qy. Okay. Finally, using 1 and 3, we can write ddt of mr dot del r dot del q dot minus mr double dot mr dot del r dot del qy is equal to f dot del r del qy. If you have not understood this, so f is our mr double dot. So that this part is, so the left hand side of 1 has now become left hand side of 3 basically has now become the right hand side, and here in this case you can see that you have ddt of, so ddt of mr dot del r dot del qy dot, that is unchanged, minus mr dot, now I had del qy r dot, now I have just a minute, no, yes, okay, so yeah, I have the same thing. I have del r dot del qy. Okay, so you can easily say that this is equal to, so this is equal to this term. Okay, yeah, okay, because actually, okay, so basically basically this is already done, because in 3 we have used this result. Because if you just see 1 said that this is ddt of del r del qy, and here I have already written del qy of ddt of r, so I have already used this result. Okay, that's why it was also, yeah. So you can see the 3 is already the main result. So finally, using 1 and 3, not 1 and 3, but using 1 and this relation, basically you can write this. Yeah, if you want, 1 and 3 in the sense that we have just replaced mr double dot as if. That is the only thing I have changed over here. Now you can easily see that you can easily write ddt of del qy dot of half mr dot square minus del qy of half mr dot square, okay, is equal to f dot del r del qy. That you can always write this form as del qy dot of half mr dot square, and this one as del qi of half mr dot square. Now what is half mr dot square? This is nothing but the kinetic energy of that particle, right? Now if the kinetic energy is T, then I can simply write that f dot del r del qy, del r vector of course, del qy is equal to ddt of del qy dot T minus del qy T. Okay, or rather you can say del T del Qi. Okay, and that is now, that is now taking a very interesting form if you do this. So up to this we have not considered any assumption of conservative force. Now if we do for conservative force, we can say the forcing term will simply be minus gradient of V. Okay, of course from our convention this is minus of gradient of the potential, and then F dot del R del Qi is minus del V dot del R del Qi, which is simply, you can easily verify, minus del V del Qi, right? Now we assume that our potential function is a function of coordinates only, generalized coordinate, that means function of q's only. No explicit time dependence, no explicit dependence on the velocities, generalized velocities, right? Qi dots. That's why del V del Qi dot is also 0. Then you can easily write this equation number 4 as like this: ddt of del T del Qi dot minus del T del Qi is equal to minus del V del Qi plus a term which is 0. So I can add any time as 0. Okay. Now this one, if you take on this side, and this one also you can take this side, then you say I define a new function chi which is equal to T minus V, and which satisfies finally a relation ddt of del chi del Qi dot minus del chi by del Qi is equal to 0, where chi is T minus V. Now just observe, T contains Qi dots, V contains Qi's. So, and T also can contain, if you want, T as well. Okay, T means time over here. Okay, so this is something which can be considered as the so-called Lagrangian, which satisfies this type of equation as we have just seen in the previous subsection of this lecture, and then one can identify that can be a proper candidate or realistic candidate for being the Lagrangian of a system, which is the difference of kinetic and the potential energy. Remember, this minus V has come because of our convention F is equal to minus gradient of V. Just check how does it look, your Lagrangian, if you write F is equal to plus gradient of V. Okay. Now a simple question: what will be the Lagrangian of a free particle and a particle which is falling freely under gravity? So one is force free particle and one is falling under gravity. Okay. So this you just think. Okay. So for this lecture I end over here. In the next lecture we will start discussing some interesting applications of this formulation. Thank you.